Hi everyone, the topic of today's presentation is the dual nature of light. Upon completing this presentation, you should be able to answer the question, what do these three items have in common? As a form of EMR, light has the properties of waves. It has a wavelength, amplitude, and a frequency. All forms of EMR, including light, exhibit the mathematical relationship between wavelength and frequency described by this equation. So, light is a wave, right? Light's wave-like properties cannot explain three important phenomena. The first of these is known as black body radiation, which is exhibited by heated metals when they emit glowing light. You have witnessed this effect when you heated copper wire in the laboratory burner flame, or when the coils of an electric stove heat up. Each color emitted by the hot metals corresponds to a different frequency and wavelength. A black body is a perfect absorber of all EMR wavelengths falling on it. It reflects absolutely no light at normal temperatures and thus would appear to be black to our eyes. It should be noted that no such object actually exists. A black body is a perfect EMR emitter when heated. The radiation emitted by a hot black body is naturally called black body radiation. Alternatively, it is also known as temperature radiation because the color of the wavelength of radiation emitted by the black body depends only on its temperature. To understand how black body radiation works, let's consider the iron coil in this photograph. Higher temperatures of this iron coil correspond to higher frequencies of light emitted. Which part of this coil is therefore hotter, the red area or the yellow? The answer is the yellow. Recall that the energy and frequency of light are directly proportional to one another. Max Planck experimentally demonstrated the mathematical relationship between energy and frequency in 1900. His experimental results led him to propose that matter gains and loses energy in small packets he called quanta. The singular form of that word would be quantum. He demonstrated that the energy of a quantum could be calculated by multiplying its frequency in hertz by a constant. According to Planck, the light emitted by hot objects was therefore quantized. That means released in packets. He showed that the energies of these packets occurred in multiples of the product of his constant and the frequency of the quantum. None of the quanta had any energies between those values. Therefore, Planck proposed that the light emitted by hot objects was quantized. That means like a particle, not a wave. Let's now turn to the second phenomenon that can't be explained if light is solely a wave, and that is the photoelectric effect. You have seen this effect when using an automatic door, such as a garage door. The photoelectric effect occurs when electrons are emitted from a metal surface as a result of light of a certain minimum frequency shining on it. The electron emission can be detected as a measurable electrical current. So why does light need to have a certain minimum frequency to be effective? There is another puzzling aspect of the photoelectric effect. Shining a brighter light of the same color on the metal causes more electrons to be emitted, but they aren't moving any faster. Dimming the light causes fewer electrons to be emitted, but again, they all have the same kinetic energy. Einstein explained the photoelectric effect by proposing the dual nature of light. That is, light is both like a wave and like a particle. He described a beam of light as a stream of energy bundles which he called photons. In this example, red light with a wavelength of 700 nanometers does not provide enough energy to allow potassium to eject electrons. However, green light with a wavelength of 550 nanometers does. Therefore, photons are massless particles that carry bundles of EMR. The energy of the incoming photon must have a certain threshold value to cause ejection of electrons because any lower energy will not be enough to break the electron's attraction to the nucleus. Since the electrons need to absorb only a certain amount of energy to be ejected, using a brighter light of the same color would only cause more electrons to escape. It would not increase the electron's kinetic energy. Einstein's experiment showed that the energy of a photon could be calculated by multiplying its frequency in hertz by Planck's constant. Doesn't that sound a lot like a Planck quantum? So yes indeed, quanta, photons, same difference. Automatic doors, as pointed out earlier, use the photoelectric effect. The system has a built-in unit that sends and receives light. When light strikes the receiving unit, it strikes a metal object that releases electrons and creates an electrical current, so the door closes. If, while the door is closing, the beam of light is blocked by, say, a person, the metal object in the receiving unit stops releasing electrons and the current is interrupted. As a result, the door is automatically stopped. And now let's consider the third phenomenon that can't be explained if light is solely a wave: emission spectra. White light, such as sunlight, consists of light with a continuous range of wavelengths and frequencies. That is Roy G. Biv, the complete rainbow. We can prove that this is so by passing visible sunlight through a prism. The prism separates the various frequencies into a continuous spectrum. That is the complete rainbow of colors. Recall that red light has the longest wavelength and the lowest frequency, while violet light has the shortest wavelength and the highest frequency. When light from an element, as opposed to white light, passes through a prism, individual lines of color are produced instead of a continuous spectrum. The frequencies of EMR emitted by a heated or electrified element separate into individual lines to give the element's bright line spectrum, otherwise known as its emission spectrum. Sodium, as seen in sodium streetlights, has a very simple emission spectrum. Neon has a much more elaborate spectrum. In fact, each element's bright line spectrum is unique to that element. Only certain colors appear in an element's emission spectrum because only photons of certain frequencies are emitted. Likewise, the element absorbs only photons of those very same frequencies. Note that the frequencies of the photons absorbed by hydrogen are identical to the frequencies of the photons hydrogen emits. The same is true for all elements. In fact, the absorption and emission spectra for a particular element fit together like a jigsaw puzzle. Scientists can compare absorption spectra from stars to the emission spectra of known elements to determine which elements are present in a star's outer layers. So how are emission, continuous, and absorption spectra produced? If you shine a white light through a prism, you will see a continuous spectrum because all of the frequencies of visible light are present. If you heat or electrify a gaseous element, such as hydrogen, until it glows and then send that light through a prism, you will see an emission spectrum. If you shine a white light through a cloud of a gaseous element and then pass that light through a prism, you will see the absorption spectrum for the element contained in the gas. Therefore, light is neither solely a wave nor a particle. It is both. Now you should be able to answer the question, what do these three items have in common? Thanks for watching.